Previously, we have established that we need to include enough control variables in the regression in order to reduce or eliminate the omitted variable bias. However, it's not necessarily a good idea to include as many regressors as possible in the model, because some variables are highly correlated with each other. The more variables you include in the regression, the more likely your regressors are going to be highly correlated. If we include two highly correlated regressors in the same regression, our model will suffer from the imperfect multilinearity problem, which will increase the standard errors of the estimates. As we learned in the previous lecture, there might not be a viable solution to fix the imperfect multilinearity problem. And hence, everything else equal, we prefer to keep the number of regressors in the model as few as possible. Therefore, when we add control variables to the model, we have to add them one by one and watch carefully how the inclusion of this additional regressor affects the estimates. This procedure is called the nested models. In your group project, make sure that you will use nested models when you run regressions. Another thing to remember when you run regressions is to make sure that the unit of measurements for your variables are easily interpretable. For example, you might want to scale down your x and y variables from millions to hundreds of thousands, if that makes the interpretation for your coefficients more straightforward. How do we know whether we should continue to add more control variables or not? Frequently, we could use the joint hypothesis test on multiple regressors to shed some light on this question. Back to the California schools example. In the first model, I regressed test scores on the percentage of English learners. The R-squared is 0.41. In the second model, I regressed test scores on STR, the percentage of English learners, and expenditure. The R-squared is 0.44. Based on the R-squared, the second model appears to have higher explanatory power in explaining the variation of test scores than the first one, but not by much. In this case, we could run a joint hypothesis test or a F-test on STR and expenditure to see whether the second model is necessarily better than the first one. In the context of a F-test, the first model is known as the restricted model because the coefficients on STR and expenditure in the first model are restricted to 0. The second model is known as the unrestricted model because the coefficients on STR and expenditure are not equal to 0. In this case, we'll specify in the null that beta 1 is equal to 0 and beta 3 are equal to 0. In the alternative, we'll specify that either beta 1 is not equal to 0, but beta 3 is equal to 0, or beta 1 is equal to 0, but beta 3 is not equal to 0, or beta 1 and beta 3 are both not equal to 0. Note that the null hypothesis only includes one scenario, that is, when beta 1 and beta 3 are both equal to 0. But the alternative hypothesis includes the specifications for 3 different scenarios, corresponding to 3 different unrestricted models. Therefore, when we reject the null hypothesis, it's still unclear to us which of the 3 scenarios in the alternative hypothesis is true. But if we reject the null, we learn that at least one of the betas for these 2 regressors should not be equal to 0. Since we are now testing 2 different coefficients simultaneously, and therefore we can no longer use the t-statistics to make inference for each variable, we have to use what's called the F-test to test both beta 1 and beta 3 at once. Additionally, since there are 2 equal signs in the null hypothesis, we say that the number of the restrictions for the f-test is equal to 2, or q equals to 2. The test statistics for the f-test is called the f-statistics. To perform an f-test on two coefficients, the f-statistics is given by this formula. What this formula tells us is that the f-statistics is computed using a combination of t-statistics and a correlation coefficient between two t's. When there is only one regressor involved in the f-test, the f-statistics is simply given by the t-statistics of that one regressor squared. To look up the critical value for an f-test, you can either look up the critical value in a f-distribution table manually or use the LHT function in R to compute the f-stats for you. The LHT function stands for linear hypothesis test. We can also specify in the LHT function that we want to use the heteroscedastic robust standard errors to conduct the f-test. Back to the previous example. To see whether we should include STR and expenditure in the model, we will restrict the coefficients of these two regressors to 0 in the null and cover the rest of the scenarios in the alternative hypothesis. If f-statistics is greater than the critical value for this f-test, then we have enough evidence to reject the null, which implies that the unrestricted model is better. The R code used to run the f-test is here. You will first estimate the unrestricted model using the LM function, and then you will use the LHT function to conduct the f-test. Inside the LHT function, you will place the restrictions for the coefficients in the second argument, and also specify that you want to use the heteroscedastic robust standard error to conduct the f-test by setting the correction method to HC1. The result shows that before the restriction, the degree of freedom in the data sample is 418 data points. After placing two restrictions, the degree of freedom in the data sample is reduced to 416. The f-statistics is 5.4, which is greater than the critical value around 3. The corresponding p-value is 0.004, which means that we have enough evidence to reject null at the 1% level. Therefore, the result of this f-test suggests that at least one of the restricted model given in the alternative hypothesis is better than the restricted model, but we have no way to tell which one. That's the limit of the f-test. We can also do a joint hypothesis test on all three coefficients in the model using an f-test. Like the previous f-test, we restrict the coefficients of all the regressors in the model to 0. In the alternative hypothesis, we specify all the other scenarios. The f-statistics from this f-test is called the overall regression f-statistics, since now we have included all the regressors from the model in this f-test. Be aware that this is the f-test provided to you at the bottom of a regression table by default in R. So whenever you're running a regression, this f-test that provides the overall regression f-statistics is provided to you by default. The line of code for running this overall f-test is here. In the LHT function, you will restrict all three coefficients to 0. The result of this f-test shows that the f-statistics is very large, around 147. The corresponding p-value is super small and statistically significant at 0.1% level. And hence, we have very strong evidence to reject the null, which states that no regressor is needed in explaining the variation of the test scores. In this case, we'll then go to the alternative hypothesis that says at least one of the three regressors are relevant in explaining the variation in test scores. Now let's pause this video and do in-class exercise number 6 and number 7. Here's another way to compute the F statistics. Assuming homoscedastic errors, the F statistics can be computed by comparing the R-square of the unrestricted model to the R-square of the restricted model. In this definition of the F statistics, the numerator is defined as the R-square of the unrestricted model minus the R-square of the restricted model divided by Q, the number of restrictions in the restricted model. The denominator is calculated as 1 minus the R-square of the unrestricted model divided by N, which is the number of the observation in the data, minus K, the number of the regressors in the unrestricted model, and then minus 1. Let's see an example. In the California schools example, the R-square of the unrestricted model is around 0.44, and the R-square of the restricted model is around 0.41. And therefore, the F statistics is computed using the R-square of the unrestricted model minus the R-square of the restricted model divided by the number of restriction, which is 2 in this case. The denominator is using 1 minus the R-square of the unrestricted model divided by N, which is equal to 420 in this case, and Q, the number of regressors in the unrestricted model, which is equal to 3 in this case, and then minus 1. The result shows that this F statistics is equal to 8.01, which is far greater than the critical value of 3. And hence, we have enough evidence to reject the null that says both the coefficients on STR and expenditure are equal to 0. You can also use the LHT function to compute the F-stat for you and reach the same conclusion. Now let's pause this video and do in-class exercise number 8. We can also use the F-test to test whether multiple coefficients are linearly related to one another. For example, we can test that the coefficients on STR and expenditure are equal. In this case, we specify in the null that beta 1 and beta 3 are equal. The null implies that these two variables have the same impacts on affecting the test scores. In the alternative, we specify that beta 1 and beta 3 are not equal. The alternative implies that these two variables have different impacts on the test scores. Inside the LHT function, you will specify in the second argument that STR and expenditure are equal and keep the other parts the same. Running this line of code, the result of this F-test shows that the F statistics is very large, around 8.94, compared to the critical value around 3. And the p-value is very small, which is significant at 1% level. And therefore, you have enough evidence to reject the null that the coefficients on STR and the expenditure are equal, implying that these two variables impact on the test scores differently. On a different note, you can also use the F-test to test other linear combinations of coefficients in the same regression. For example, you can test that STR is equal to 2 times expenditure. You can also test that STR is equal to 2 times expenditure plus 10. You can even test that STR is equal to expenditure plus the percentage of English learners, for example. But you cannot test that STR is equal to expenditure square because the relationship is no longer linear. Now let's pause this video to do in-class exercise number 9 and number 10.